In traditional automotive safety, isolating critical systems was a matter of physical distance. You separated the computers. The electronic control unit running your anti-lock brakes sat in its own housing with its own wiring, ensuring a software glitch in the radio couldn't interfere with the car's ability to stop. Modern autonomous driving requires processing power that has forced these separate computers onto a single piece of silicon, the Mixed-Criticality system on chip. Now, life-saving braking algorithms and standard infotainment apps reside on the same microscopic real estate, sharing the same circuits and memory channels. This integration challenges the mathematical foundation of safety, specifically ASIL decomposition. The theory relies on redundant pathways. If one side fails, the other takes over. Statistically, the probability of two independent systems failing at the exact same microsecond is low enough to meet the highest safety standards. But inside a microchip, independence is often an illusion. Dependent failure initiators are the shared physical connections, like a common voltage regulator or a clock generator, that bypasses this redundancy. A single fault at one of these junctions infects both systems simultaneously, causing them to fail in lockstep. In a highly integrated environment, physical proximity creates invisible vulnerabilities. Mathematical redundancy is only effective if the backup doesn't share a single point of failure with the primary system. This lack of isolation leads to cascading failures, a process where a mundane task crashes a critical one by exhausting a shared resource. On a single chip, the primary bottleneck is often the L3 cache memory. If an infotainment app begins streaming 4K video, it can begin flooding the shared cache with data, overriding memory lines used by other processes. This creates timing interference that ripples across the entire chip. For a sensor fusion algorithm, this interference is fatal. It may have a strict 100 millisecond deadline to calculate a trajectory. Because it is forced to wait for memory access behind the video stream, it misses that deadline, causing a failure in the autonomous control loop. Engineers prevent this by establishing freedom from interference. They use hardware firewalls called memory management units and hypervisors to partition resources. If an app tries to exceed its allotted memory or time budget, the system identifies the breach and throttles that process to protect the critical safety functions. Spatial and temporal isolation requires a system architecture that can prioritize a 100 millisecond braking command over any amount of background data traffic. Even with memory firewalls, systems remain vulnerable to common cause failures. These occur when a single external event, like an electromagnetic spike or a shared power failure, knocks out the main processor and the backup processor at the same time. This risk extends to the sensors themselves. If a car uses two identical cameras for redundancy, a single environmental factor, like a wall of dense fog or a specific angle of direct sunlight, blinds both sensors at once. Redundancy fails because the two systems are vulnerable to the exact same physical triggers. To counter this, engineers employ heterogeneous diversity. This means pairing different physical principles, such as light-based cameras with radio-based radar and laser-based LiDAR. By using different hardware and different software logic, you ensure that no single environmental condition can neutralize every sensor. Identifying these shared vulnerabilities requires more than just a schematic. Using SysML v2, engineers code the system's entire logical and physical architecture into a digital matrix. This allows them to run automated fault injection tests that simulate failures at every shared junction of the design. Surviving a common cause failure depends on intentional architectural diversity, ensuring that no single logical bug or physical event can disable the entire vehicle. While isolating electrical and logical faults is governed by established engineering rules, the introduction of artificial intelligence shifts the focus from how a chip is built to what that chip has been taught. The SOTIF standard, or ISO26262, addresses functional insufficiency. This is a scenario where the hardware and software have no traditional bugs, but the system's inherent limits are exceeded by the environment, like an optical sensor being rendered useless by a sudden whiteout snowstorm. Under ISO 8800, engineers must account for training data dependencies. Missing specific examples creates hollow nodes, hidden vulnerabilities. If data lacks pedestrians in rain, an AI blind spot forms. Hitting that specific real-world gap collapses the entire perception pipeline. To trust these systems, the industry must look past the wiring. Safety now requires severing dependencies within the silicon, within the physics of the road, and within the very data that defines how a car perceives the world.